Hello, my name is Rob Reynolds. Welcome to Math 073. Today we begin our Chapter 7. The very first section deals with quadratics, and we're going to be looking at how to solve quadratic equations and also talking about completing the square as a technique for solving quadratics. And then we're going to look at a couple word problems as well. So quadratics are anything that deal with x squared functions. They graph these nice parabolas, and oftentimes we end up taking the square root, and remember, every time we take the square root in order to solve something, if you write that square root sign, then there are always two answers, plus or minus 3, because 3 squared is 9 and negative 3 squared is 9 as well. So the standard form is this ax squared plus bx plus c, where a, b, and c are just nice coefficients. C is a constant. So taking a look at our first example, again, I'm going to take the square root of both sides, so I should end up with two solutions here. The square root of 36 is plus or minus 6. What that literally means is those are x-intercepts. So if you were to graph this, you would have an x-intercept at 6 and negative 6, and that's actually where the function is crossing. So just to try to make a relationship between the actual graphs and the numbers that we're crunching, if you were to go to your calculator and graph, well, I would have to solve for this. First, let's go solve it for x squared. I'll subtract off the 36 and set it equal to 0. So the real function that I'm solving for is, instead of x squared equaling 36, if I subtract that off, I'll get x squared minus 36, and we'll set that equal to my function. So looking at the graph of this, I'll hit zoom 6. Now, I know the y-intercept is going to be negative 36 and it's way off, but I don't really care about the y-intercept right now. I'm really interested in those x-intercepts just to show you what I'm solving for. If you hit trace 6, 0, those are called x-intercepts. So solutions are really x-intercepts. They're the same word. Sometimes we call those x-intercepts solutions. Sometimes we call them x-intercepts. Sometimes we call them roots. And sometimes we call them the zeros of the function. And you could actually solve for these roots or the zeros by hitting second calculate and go to number 2 and guessing to the left. So I'll guess to the left of 2. I'll guess to the right, which is 8. And then I'll guess right. I know the answer is 6, but I'm going to type in a 5 just to show you it doesn't really matter, and it gives me the x-intercept. So either roots, zeros, solutions, or x-intercepts, it means the same thing in math. So plus or minus 6 is the solution here, and that's what the author's talking about here, how those plus or minus 6 relates to the actual graphs. This is just another example where that if you take the square root of both sides here, we're just going to get plus or minus 5 for solutions. So if it's not in that form, then we have to do a little bit different method. I'm going to try to factor this and then set each factor equal to 0. So I see from here the greatest common factor is 2x. So I'm literally going to divide each term by 2x and factor that out. So if I factor out a 2x, what's left is 2x plus 7. And then I'll set each factor equal to 0. So 2x equals 0 when x is 0, and 2x equals negative 7 when x is negative 7 halves. So to find the x-intercepts, those are the x-intercepts, 0 and negative 7 halves. And you could, again, pull out your graphing calculator, type that in, and actually calculate if those are the solutions. Just hit trace 0, enter, and make sure that that's a solution. So you can check all of these answers on your calculators. So anytime you see something in the x squared equals some constant d, there's two answers, the positive square root and the negative square root. Let's look at another example. If I divide everything through by 5, it's an equation. I can do whatever I want as long as I do it to both sides. I get x squared equaling 3. And then if I take the square root of both sides, I'll just leave it plus or minus the square root of 3. Again, your calculator will check this very nicely. All you do is you type in 5x squared minus the 15. I'm going to delete out. I didn't do that very good. Let's try it again. 5x squared minus the 15, setting it equal to 0. I'll hit zoom 6. And then to check my answer, I'm just going to hit trace the square root of 3. And I'll press enter, and sure enough, that's a 0. I can look at the y value and see that that's a 0. And here's the author's solution. If you wanted to change that into decimal form, we certainly could as well. For this one, I look for a greatest common factor. And after I decide that there is no GCF to factor out, then I'll go ahead and isolate the x, getting the x term all by itself. -9, dividing through by 16, and taking the square root of both sides. So remember, every time you write the square root, you get 2 answers. And we learned in a previous video that every time you take the square root of a negative, an I pops out. So this really is an imaginary number, because this is written as the square root of -1, the square root of 9 over the square root of 16. So it's I times 3 over 4, which you would probably write as plus or minus 3/4 I. Remember, there's always 2 answers every time you write that square root. So we can have imaginary roots, and what that looks like in terms of the graph is it does not cross the x-intercept. To undo squaring, I'll square root both sides. And the square root of x plus 3 squared is just x plus 3. But over here, you have plus or minus 7. So, excuse me, plus or minus the square root of 7. So when you subtract off 3, you have -3 plus or minus the square root of 7, which you cannot combine. And again, you can type that into the calculator and check pretty easily to see if that really is the solution or not. I'll do this one more time. I'll type in x plus 3 quantity squared. I'm going to subtract off the 7 to set it equal to 0. I'll zoom 6 to get a graph. And I'm interested to see if these are the correct zeros or not. So I'll type in -3 plus the square root of 7. Now let's hit trace. -3 plus the square root of 7. And I'm looking for a 0, and sure enough, my calculator gives me a 0. And you could try -3 minus the square root of 7 too. It should work. This is a tricky problem. Normally I tell students to, when they see an x squared in an x term, is to set it equal to 0. And try to factor. So if I were to subtract off 17 from both sides, I would get a -1. So in this particular problem, I would have to use the quadratic formula. X is equal to -b plus or minus the square root of b squared minus 4ac, all divided by 2a, because there are not factors of 1 that differ by 8. A different strategy that I just want to introduce to you is looking at the left side. This does look like a perfect square. So if you were to try to factor just the left side and leave the 17 alone, factors of 16 that add up to 8 are 4 and 4. Signs are alike. You keep the common sign here, so signs are alike. They're both positive. So that's really x plus 4 quantity squared equals 17. This would probably be faster than this blue quadratic formula, because now I'm back to just taking the square root of both sides. So if you can factor just the left side as a perfect square, this problem is much easier to solve than the quadratic formula. We should get the same answer, but it's just less work. So look for that trick by trying to factor maybe one side and then taking the square root of both sides. And that's exactly how the author went about solving this as well. Not all quadratics can be written as a perfect square. Quantity squared equals some number. So we could use the quadratic formula, but another strategy would be completing the square. And that's what we're going to introduce to you for the rest of this video, where you take half of the middle term, I call it the star step, and square it to help complete the square. The goal is to get it into quantity squared. So the rule is, for completing the square, half that b term, remember, it's ax squared plus bx plus c equals 0, so that's b term is the number in front of the x. So if I take half of 10, that's the b term, and square it, I'll get half of 10 is 5 squared, and that's 25. So I would rewrite this as x squared plus 10x plus some number. And even though 4 is a perfect square, I'm going to subtract that off because it's not the perfect square that I need for the 10. So I'll throw it to the other side. And then I can see that that star step says take half of this 10, which is that 25. So, but if you add 25 to the left side, you have to add 25 to the right side. You can do anything you want to an equation as long as you do both sides. So this side is my perfect square. Factors of 25 that add up to 10 are 5 and 5. So you could write that as x plus 5 quantity squared equals 21. And then when I take the square root of both sides, I've got x plus 5 is equal to plus or minus the square root of 21. And my final solution is negative 5 plus or minus the square root of 21. So that's probably the easiest way. Again, you can use the quadratic formula if you choose, but I'd like for you to try completing the square. Sometimes it gets a little bit more difficult if you have a leading coefficient, because you cannot do that star step. Remember, the star step I call that half the middle term and squaring. You only do that with a leading coefficient of a 1. So if you have a 4 out front, you probably want to factor that out first. So it's going to be v squared plus 4v. I'm going to create a blank here, is equal to 65 plus blank. So now instead of taking half of 16, I'm going to take half of 4 and square it, which is another 4. That's that magical number that I'm looking for. But instead of adding a 4 to this side, I actually created 16 on the left side. So these numbers aren't always the same. It should be the same weight. So over here with the leading coefficient of a 1, I didn't have to worry about that. I was adding 25 to both sides because I wasn't distributing anything. I'd never factored anything out. But over here, the total weight that I've added is 16. So on this side, I'm left with 4 times the quantity v plus, and it's always just this number, half the middle term, quantity squared, is equal to 81. And so then I'll take 81 and divide by 4, which is not a nice number. So I'll just leave it as a fraction, 81/4, because the next step is to take the square root of that, which it is pretty nice then. If I take the square root of 81, I'll get 9, and if I take the square root of 4, I'll get a 2. So my final solution is negative 2 plus 9 halves, or negative 2 minus the 9 halves. I probably wouldn't leave it like this. I'd probably just change that into decimal form. So this would be a 2.5, and this would be a negative 6.5. If you want to change those into fractions, you could. But again, completing the square, we take half of the middle term, and then make sure that you're adding the same weight to both sides, which does not mean the same number. And the author has the same solution here. Completing the square, again, with a leading coefficient, makes things a little bit harder. I'm going to take the 1 and throw it on the other side. I'm going to try to factor out a 3. Now this is of the hardest type of example because I'm actually going to end up with the b term to be a fraction. So if you factor out a 3, 7 doesn't divide nicely by 3. So I'll just leave it 7/3 x. I'm going to add some magical number that will help me complete the square. That's the goal. And then I'll equal that to negative 1 plus some number 2 that has the same weight as the other side. So when I do the star step, which is half the middle term, well, instead of taking half, I'll multiply by a half and then square it. So that becomes 7/6 squared, which this magical number here is 49/36. And the reason why I call it a magical number is because it helps me complete the square, which was really the goal. But instead of looking for factors of 49/36 that add up to 7/3, I know it's just always this number here. So I'm going to put this 7/6 down here. I always just keep this sign here, which is a plus, and x. So half, the number before you square it is always the number that goes in this quantity here. Now be careful. 49/36 was the number that I wrote in this blank over here, but I think I need to multiply that by 3 in order to get the number that I'm going to put over here in the blue. So over on a little scratch paper, I'll multiply 3 times 49/36, and I'll try to cancel. 3 goes into 3 once, 3 goes into 36 12. So this is really a 49/12 on this side. So I'll get common denominators here. This is negative 12/12 plus 49/12, which is 37/12. The next step is to divide through by 3, but that's the same thing as multiplying by 1/3. And so this will cancel over here, leaving me with x plus 7/6 quantity squared is equal to 37 back to my 36ths. And then when I take the square root of both sides to get rid of my quantity squared, I'll have x plus 7/6 is equal to plus or minus the square root of 37 divided by 6, because that's the square root of 36. And my last step is to subtract off 7/6 from both sides. So my final solution is x equals negative 7/6 plus or minus the square root of 37/6, which you could write it as negative 7 plus or minus the square root of 37, all divided by 6, if you like. Some of you are going to think that the quadratic formula is a little bit easier on this problem, but again, if the directions say complete the square, then this would be the process that we would want to go through. Here's how the author chose to solve this. You can pause the video here and look at their solutions, but I believe they ended up with the same answer. So here are some steps to help you complete the square. The important step is, I call it the star step, taking half that middle term and squaring it and making sure that you're adding that to both sides. But remember, you can only do that star step or completing the square with a leading coefficient of a 1. The last example is a word problem. We have a building that is 1,670 feet tall. And the question is, how long would it take for the object to fall to the ground? Well, this is kind of a physics problem, and you need to know something about gravity. On Earth is defined as negative 32 feet per second. So if the problem would have been in terms of meters per second, I'd use the negative 9.8. But since they said feet per second in this problem, the actual formula here is 1/2 of the gravity. So if I take half of the 32, I'll get this negative 16. So we're going to be using this formula. S, standing for the distance, is negative 16t squared. V sub O is the initial velocity, which I believe we had initial velocity of 0, because we were just standing on the building letting an object free fall to the ground. And then H would be the height. And I believe the height of this was 1,670 feet. So to solve for t, which was the goal, because it said how long, that's the time that I was looking for, does it hit the ground, I would add 16t squared to both sides and divide through by 16. And I'm not sure what decimal that number is, but if I take the square root of both sides, I could just use my calculator. And again, you're going to get a plus or minus, but the only thing that's going to make sense is the positive, because time can't be negative. So again, the author just says a formula that fits this situation, and they don't really do any explanation of why you're using S equals 16t squared. But the reason is because of this formula here that you'll learn in a physics class, and has to do with gravity. Eventually they get down to the same equation that we used and the same solutions. And then here's their check that they're performing. It's nice when it's a word problem to go ahead and state the final solution and making sure that you're using proper units. I hope you found this video helpful. If you have any questions, feel free to email me.